怎么？
乱码，太大了，
大叫。
我操！哪知道那个你在那个疯，
没有强，看你的 IG 精神状态很差
啊？
看你 Instagram 精神状态很差。
没有
跟谁吵架了？
啊？
跟谁吵架了？
没有，还跟全部人吵架。
好吧。
因为在播那个对啊，天天炸。
没有，你有一条被炸的，下面写了一句什么跟谁吵啊，跟谁吵，跟谁吵，跟谁吵。
对啊，
所以发生啥了？
还没有发生。有发生要发生。
所以为什么要发生？
老板上面有头吗？
对啊，
老板还有老大，还
有校长呢。你要去跟
那吵死
啊？
你觉得还可以？觉得可以进，我们就会来这里吵。
所以你要吵什么？
觉得可以吵，你要跟他拿过去。
No, I just need to be part of the band because I lost that from the consultant. Alright.
是不是老板接的？
然后我不给他做，
因为那个老大跟老大有可能那样，
他要影响
哦，他的开游戏，其实老板推给他，老板推给老大。
我叫老板行。
给老板吃
啊？你觉得？谁谁谁？
你都不行的，现在
他人太好，被欺负。
被老大欺负，
不是被谁谁谁欺负吗？
被老大欺负了。
我还以为被谁谁谁欺负。
谁？那谁会欺负他？他不会欺负他。
OK。前天应该不会有上去的8点几开始，
反正没有几天。
我在弟弟懂为什么在我讲第四个，我只是发现，我只是想，因为这个会有，
只是他平时去那个
可能是
缅甸
跟
还可以出来。
对，你看你去那里做工，去那里做工，那你愿意去做工？
我是全部被抓去在那边做的，
不是被抓的，他是来
被带走的。我只能
然后去做杂工。
对着来，让我们那个时间是才不错的想着。
这很离谱哎！那他那边的整，你拿个钱多好。
这玩滚头，结果学长在看，
好像简单嘛。哇，很棒！
你没有看到那个打分吗？你反正看着我看，
那你把那个
他因为要洗澡也三角洲，洗澡一个大班。
伊朗人啊，
这是一个中国的一个人啊，还有让我们啊，
哎，你怎么可能啊？
也解释
没有那个可能。哎，导弹很好，这样。哇，
了解导弹这样，
跟一个导弹砸了一个，
为什么？嗯
啊，
我们就不交什么费了。
对呀、Okay, let's start. So in the middle of this break, right? So we assigned to have a class on Saturday, okay? So if your group mate is not here yet, please call them and call them come here and find it. So we are close to having an idea of reading course. Do you still remember the idea of reading course I mentioned last time? Yeah, remember? Aditya, what's the idea of a reading course? So people still will read and then come on and explain, right? Okay, so we're gonna make this happen on the 4 replacement class we have to do. Okay, so you guys have to present. Okay, so everyone have to be present. Okay, so present what you have learned. Okay, try and teach. Okay, try and tell people okay about some new knowledge. Is it hard or not? Do you find it hard? Super hard. Okay, so you should appreciate your lecturer when they are standing and they also prepare a lot of time. Okay. Yeah, so you just prepare 20 minutes, right? Very long. Okay, so it's the same preparation. And I haven't touched your assignment yet. No chance to pass it, touch it, because I'm gonna finish your exam masterpiece. Masterpiece, right? So once I finish, I'll let you know what you need to focus on and then what you can bring into the exam. But basically, it's a double-sided A4 handwritten section. Okay, so I guess your timetable is out already, right? And general topology and algebraic geometry is a consecutive date because our class got graduating students. Okay, so it has to happen during the student study week and the first week of February. So that's why your exam is earlier. Okay?
I hope every class can do it.
Yeah, that's one thing. For most graduating class need to finish in the first week of exam. Okay, hopefully after this week I'll be more free then I'll finish all your assignment routine. For the last assignment, right? I'm not sure I have time to come up with 2 or not. If not, we will come up with 1. And then I will give you a longer time and then the difficulty might be harder. Okay? Yeah. Sorry? Huh? Oh, we still have 2 more time to go, right? If I don't have time to do 2, maybe we'll just do 1. Okay, we'll do it as a take-home exam level. Yeah, because the last 2 sections we won't be tested in the final exam. Okay, so I'm slowly taking your exam away, Adrian. You guys say don't like exam, right? I slowly shift the exam away. Yeah. But you have to do it properly. Okay, it's not just for me. Okay, I think that's it for our admin stuff. Okay, so what's the planning for the rest for the singularity chapter here? I will do an algebraic version of dimension and then see how it links to a dimension of variety. And then last week we will do is a blow up. I'm still reading on that part. Hopefully I can come up with something either tomorrow or next week. And after blowing up, then we will do Bison. And then I think that's the last thing we'll do this course. And then we will wait for your presentation. Okay, let's start. So today we will talk about the algebraic factorization of a dimension of a variety. Okay, so let's start from what we have done. Let's start from the Noether normalization theorem. Okay, what does Noether normalization theorem tells you? Anyone? You have to do assignment on this one. What does the theorem give you? Sorry? What did you say? You can find algebraically independent element from where? From what kind of algebra? Finitely generated? Finite? Module? Huh? K-algebra? What kind of K-algebra? Any condition of K-algebra? Finitely generated? Is it? Try and check. Check. Yeah. Just finitely generated is enough. Okay. All right. So if you start with some fraction field, okay, of some coordinate ring, okay. So what can you find is you find a field extension, okay, of your K in between your field K and this quotient field here. So what's the business here? So we know that K over KT should be algebraic, and KT over the field K is purely transitive. Okay, so what does this mean here? We didn't really talk about this word, right? But you should know that from the theorem, it is generated. So that is generated by algebraic independent. What does it mean to be algebraic independent? Not algebraic dependent. Algebraic dependent means what? Yes, there's a polynomial that govern the relation between these elements. So this polynomial here, right, doesn't require it to be monic. Doesn't require it to be monic. But if you are in a field, okay, if you have such polynomial, then it must be unique because the elements are invertible. But let's say if you are in a ring extension, just normal ring there, then if you require this polynomial to be monic, it is what we call an integral. Okay, I put it in my tutorial already. Okay. So there's a subtlety here. So in field, algebra extension and integral extension is the same. Okay, but if you move to ring, okay, then this polynomial might not be monic. Okay, if you require the polynomial to be monic, it is for the integral. Integral extension. So I already cooked up your tutorial 889. So please have a look and study. These tutorial represent what skill you should learn in this course. Okay, other than the lectures. Okay. All right. So in this case, we could write KT as K of field generated by external x. Okay, because this is a field extension, so it's a field. Okay. So let's make some definition here so that we are on the same page. So we will write K portion out by AM here. Oh shit. You don't know this notation, right? Okay. So let's do this notation then. This is a subset of K. Okay. We call it is an algebraic extension. Okay. Meaning what? Meaning every element in K take away this subfield here. Actually, it's algebraic. Okay, last time we defined what is algebraic mean, the element to be algebraic, so that they satisfy some polynomial equals 0. Okay, then how about this alpha I here? We will say that this alpha I, the span, okay, span the transcendental, because there's no algebraic relation between them, meaning polynomial relation between them. Okay, and moreover, if we found out that they are really algebraically independent, then this set is what we call a transcendence basis. Okay, so span and dependent, okay, algebraically. So this is a bit like a generalization of vector space basis. Okay, but here we are not using the linear dependent relation where we just use linear combination, but here we are allowed a polynomial relation. Okay, what's the difference between polynomial relation and linear independent for a vector space? Now, what's the difference? In polynomial, you can take power, or you can take products. And so it's really an algebra version of vector space. Okay, then what do you do after defining basis? You say that two bases will always have the same number, okay, and then we call this number the dimension. Okay, in this case, we call the cardinality of a transcendent basis to be the transcendence degree. Transcendence. Okay, which we denote as tra degree. Okay. Okay. So of K over the field. Okay, tra degree. Okay, so what we're gonna do next is following this slogan here. You should remember. So the dimension, okay, of a variety should be equal to the transcendence degree of its function field. Okay, so there's a relation between a variety and its function field. Still remember what's the dimension of a variety again? Or maybe to be precise, yeah. What's the relation between sorry, what's the definition of dimension of a variety again? Minimum dimension of vector space. Okay, sorry, minimum dimension of vector space. What vector space? Tangent space. Okay, sometimes people will call that a Zariski tangent space. Okay, Zariski tangent. So okay. Right. So let's prove the simple case first. Okay, so the simple case is the dimension of a hypersurface. So we always do things starting from hypersurface because it's just zero set of one polynomial. Actually, it's equal to the transcendence degree of its function field. Okay, last time we already know what is the dimension of a hypersurface, right? So anyone still remember what's the dimension of hypersurface? How do we find the dimension of hypersurface last time? You do it. Okay, look at the knot there. Check your knot. I also forget already how to find them. What's the dimension of it? Check your knot. Anyone found it? Yeah? Do we prove anything about hypersurface or not? Didn't do it. Supposingly, we should have it. Huh? Is it? Oh, weird one. Yeah, let me check. Did I miss out? We didn't do dimension of hypersurface. Hey. Wait, how come we missed that out? Yeah? Sorry? Huh? Hey, I thought I did it. Mm-hmm. What do you mean? Mm-hmm. Hypersurface we got one then. So which one? Huh? Uh-huh. You mean just compute the tangent space, huh? Okay. So if you compute the tangent space, what do you get? You have a F. Then? Huh? You got a F, and then you do partial derivative, right? And then you check at every point. And then how do you calculate? I think we did it right. we did it in here. So what happening here? So we got F, then we think that if the rank of this matrix here, so maybe you look at the coefficient, is 1, you can only if del F over del Xi is 0, non-zero. The minimum, what's the minimum you can get here? The claim here is n minus 1. Because last time we proved that dimension of V is n minus something, right? N minus the dimension or the rank of this polynomial, right? If it's singular, what happens? If singular means what? What can you tell about this line here? It is a negation of this line, right? So for every I, the partial derivative is 0. So the coefficient all 0, then what are the points can satisfy? Actually, when your point is singular, the dimension is the whole space. It's larger. And so at most you could get for your rank is 1. Because you only got 1. And so dimension of V is n, right? N minus the rank of the coefficient, the matrix coefficient. I think someone called this Jacobian matrix. Okay. Makes sense. Does it make sense? Any question? No question? Question? Feel free to ask now. Okay, I won't score you. 是被骂怕的那个，我其实也是被骂怕，但是我还是想回应。你以为我是个反骨的小孩子 ？Okay. How about the other side? How to compute the transcendence degree of this function field? Hey, sorry. Okay, how about the transcendence degree of this function field then? How to compute its function field? How do you write down the coordinate ring of V? Hijack. What's the coordinate ring of V? How many variables you have? It's a quotient ring, right? So what's the how many variables you have? Okay, quotient out by what? Huh? Ideal generated by what? Huh? Huh? IV, yeah. What's IV in this case? What's IV in this case? Huh? What's IV then? IV is what? Function that vanish at V, right? So how you get this V? I don't know, but I mean, what's IV? I'm asking you what's IV. Ideal generated by F. Doesn't make sense. Ideal generated by F. IV is hydrogen by F. Why? Why, Eric? I said that V is a surface defined by function F. What does this mean? It's a zero set of F. Zero set of F means what? Is the point that make F vanish? This IV is all the functions that make V vanish. Okay. Oh, please, think about it. Okay. So, well, we have one function, right? Okay. So, possibly by rearranging, possibly numbering, we assume that F contains the variable x1. Okay. Then how do we invert it? Okay, so how do we invert this kv here? So we just write it as k. Get s2 of sn. That portion. Okay, so that x2 xn form transcendent basis of okay. Okay, because there's only one polynomial that governs this variable here. Okay, and then you just pick one. Okay, pick one such that one is dependent on the others, and then the others you can just take with them. Okay, because this f here will give you the polynomial relation between these. So in this case here, the transcendent degree is of kv here is n minus 1, okay, which is dimension of it. You only have one function, okay, that have an algebraic relation between n variable. Okay. Okay. Any question? So you're trying to invert. You try to invert the polynomial, right? Or the polynomial, and you can't really invert the xi, right? Because your xi. Let me think. So put it. So f will give you a relation. F will give you a relation. Okay, and then everything that equal to f or multiple of f is 0. Okay, in the coordinate ring of kv, and then you try to invert element inside here. So let me think now. Maybe the question here is why can you invert x1? Invert x1. You can't invert x1. So maybe the question here is maybe why can't you invert x1? What happened you invert s1? What happened if you invert s1 here? Okay, maybe let's left this. Think about this. Maybe we can talk again tomorrow and think about this. Okay. Next. So previously we defined a tangent space to be the analysis way to define it. Okay, we get a partial derivative. Okay, but now we'll give some description using maximum ideal. Okay, in the local ring. Okay, so some algebraic version of a tangent space here. I think this is more to a Zariski tangent space rather than the analysis one. And then we will see how regularity, singularity concept appear without looking at the embedding, okay, of affine variety. So there's a theorem here, but to prove this theorem, there's some algebra statement that we need to know first. Okay, let me write down what we are trying to show here. So there's an isomorphism of vector space. Okay, first on one side we have TPV, okay, what we defined last time. Okay, all the point that makes your partial derivative equation 0. Okay, we will show that this is isomorphic to another vector space. Okay, so this vector space here is a home space. Okay, so homomorphism from this MP quotient MP square to the field. Okay, and then this is what we call the dual space. Okay, TP over MP square. Later, I think we should see that MP over MP square is a vector field, vector space. And then what does it mean by a dual of a vector space? Okay, just means that function mapping up from this vector space to the scalar field. That's it. So you map into K. That's all. Okay, nothing special here, nothing fancy. So if I give you a vector space, okay, you can look at the function from the vector space to scalar field. So how do you think about this function? It's just like evaluating the vector. I don't know how you evaluate, but just evaluate. Okay, give you a vector, give me a number. So one, if you have taken ALA before, this is the dual space you have seen before. Okay, so the interesting part here perhaps is the dual space of a vector space still a vector space. Okay, actually it's not too hard to think about. Think about function, addition, function, scalar multiplication. It satisfies the vector space. But it's not hard to write it down. Okay, so what's MP here? I hope you ever forgot. MP here is F over G in K bracket V, so it's a function field such that FP equals 0 and then GP is not 0. Okay, so FP here equals 0 is quite how to say quite important here. This is exactly the unique maximal ideal. If FP not 0, right, then this whole thing will become invertible. Then you'll get back the whole ring. So this is a subset of the stock, right? The stock, the local ring here. And obviously this local ring is a subset of KV again. And then we'll say that this isomorphism, right, is actually natural. So natural in the sense that we don't care about a basis. Okay. Before proving that, I think there's one algebraic statement you need to agree with me is if two vector space is isomorphic, then the dual of two vector space should be isomorphic as well. In ALA did this proof before. No, don't know. Huh? Forget. 有做过啊？啊？没有 Not sure. So let's say you have vectors isomorphism between two vector space means what? There's a map between them which is surjective and injective. Okay. But if you want to show that the dual, okay, the two dual are isomorphic, what do? You also produce a map that is injective and surjective. Okay. But isomorphism in dual means what? You need to send a map, let's say V and W. You need to send a map that evaluates V to a map that evaluates W. Is it possible or not? You want to change your domain. Still remember the idea of changing domain in this class? What do we call it? Pullback. Can you pull V back to W or not? Is it possible? Is it possible to pull back or not? Just now I tell you that V and W are isomorphic. Can you go V? Can you go from W to V? Oh, sorry. Yeah, so you not only can go from V to W, but you also can go from W to V, right? So there are two directions to go. Okay, so meaning if you want to make a V dual element become a W dual element, you just pre-compose by your isomorphism. If you want to make your W dual to a V dual element, we call the star dual. You just also compose with the inverse of your isomorphism. Make sense? And then just prove that these two are inverse of each other. But yeah, obviously inverse, right? But you try to write down the order you apply is match up. Okay. Okay. So one thing to prove is if V isomorphic to W, then V dual is isomorphic. I'm gonna try and write this down to prove. Okay. So I guess we could start the proof now. In case I forgot some statement, then we will do on the spot. Okay. So for simplicity, we just assume P to be 0. Otherwise, we just move it by translation. That's it. Don't call it origin. Sometimes we reserve it for some other things. Okay, it's the 0 point. Okay, so that the MP we consider here is very easy. So the MP is just ideal divided by x1 up to Sn. Okay, if not, we just do shift. Okay, if some other, if imagine there's P1, P2, and Pn. So what's your maximum ideal? Unpaid. If my P is non-zero, P1 up to Pn, what's my maximum ideal correspond to this point? Pi up to Pn. So what's the corresponding maximum ideal then? Maybe you can call out someone who can help you. Huh? You call your friend. Adrian. What's the maximum ideal correspond to P1 up to Pn? Point divided by P1. Yeah. What's the point and maximum ideal correspondent here? You work now 7 some. No idea. 他教你啊，教你修修啊。 the maximum ideal that corresponds to this one.
xi minus pi.
The ideal here by xi minus pi. Okay, you should always remember the evaluation homomorphism that give you this correspondent here. Okay, because if you have a ring, polynomial ring, portional by this xi, right? Okay, ideal by this si, you will get a field. Okay, you will get a field. And then the kernel is this maximal ideal. Okay, so this is the maximal ideal. And then let's consider a bigger dual here. Yes. Okay, yeah, sure. Let's use different. Yeah, a bit different. So let's put this as a capital M. Okay, so next we look at a larger dual space here. Let's look at the form from Kn to K. Okay. Okay, so this is the dual space of Kn here. So we look at all the map that evaluate Kn, okay, to K. So who generate this map? Who generate this map here? Who generate this map? A very easy one is the coordinate function. Okay, so the coordinate function S1 up to Sn. Do you believe that these Si to Sn will generate a number for you or not? Do you believe? So we call this a linear forms, which means nothing special here. It just means that it is a degree 1 linear, degree 1 element. Form is a function. Do you believe that this coordinate function will generate number for you or not? Do you believe? How? Jingsen. How? A1 to AN, and then. So X, what does Si do to a point in Kn? So go back to it read you the ith coordinate. Ith coordinate. Okay, depend on what Si you use. So it's a projection. These Si are projection. Okay, this definition of these Si. Correct or not? Let's say you have R2, right? You call the point xy. But what's really xy? X meaning what? I'm reading out the first coordinate. Y meaning what? I read out the second coordinate. But first coordinate, second coordinate, are they real number or not? If I give you a real one, they are real number. So these are just a projection and these coordinate function. Okay, read out the coordinate. Okay, and then each coordinate is k, right? So that I tell you there's n copies of k. Okay. Okay, so your function should be built up by this coordinate function here. Okay, so they are actually basis for your function space here. Okay, because the com we consider here is really because these are two vector spaces, right? Okay, so the home we write here is the linear vector space homomorphism, okay, which is the scalar is few k, okay, the scalar is few. Okay, so how to get another number? Basically, you just play around with the n copy of numbers, and then how can you play around? You can only play using a linear way because this is a vector space. Okay. All right. So for all f in kx1 up to xn, what do we have? We have the linear part of f, right? Let's call it a linear function, fp1 here. Okay, basically this is what we know for our building our tangent space. Okay, and then this is a very valid element in Kn star. Okay, because if you put a point in, it gives you a real number. In particular, we obtain a map. Okay, this map is going from a different direction. So actually, if you get any function from MP, get maximum ideal there, and then going to this Kn star here, we'll send the f to its linear part. Okay. So I give you a f, calculate the linear part. You can see this as another map. Okay. Moreover, this is a linear map because derivative is linear. Okay. Derivative is a linear operation. Okay, so it's a linear map. First of all, this map is surjective. Okay, this map is actually surjective here. Okay, so to show surjective, right, you just need to be able to build all your basis elements. But we know that the basis element in Kn star is just coordinate function, right? So which function map to coordinate function? So what's the function that you input, and then you do this partial derivative, and then you output the xi? Just the coordinate function itself. Okay. Why? You put xi into that partial f partial xi. Which one, when it survives? It survives when xi is okay, sj equals to when j equals to I. And then 1 evaluate on 0 should be 1. So time xi, you get back your si. Okay. And then how about kernel? Kernel is a very important thing here and very interesting. What's the kernel? What's the kernel here? What's the thing that evaluate to 0 polynomial in this case? You should remember how to make it 0 from this formula here. Lydia, how to make this term into 0? If you see from this definition, what can you play around here? What did you learn from this definition? What do you need to do? You have a product, you have an evaluation. When can you always make sure these terms are 0? Xi, you cannot make it 0 already. Xi is just a coordinate function. But there's some place you can make it 0, right? This evaluation. What's the thing that can evaluate to 0 at 0? Who said constant function can evaluate to 0? Who can never evaluate to 0? No matter what point you put it. Polynomial is not constant term. But now you need to go back another step, right? You have to talk about f instead of partial f. So you need to, after derivative, get no constant term. So what is the order? At least second order. Okay, so the kernel is what we call the MP square here. Okay, since for FP in MP, okay, we have FP1 equals 0 if and only if all terms of F have order at least 2. Okay, so at least 2 means you need to stay inside MP square. Okay, every term need to be generated by degree 2. Yes. Let me think. to have constant term. You mean for f itself? You mean for f itself? Okay, let me finish here first. So let me finish last line. So if this is true, then we'll induce an isomorphism of MP over MP squared. But in this case, do we really care about constant term or not? Because our MP is generated by the coordinate function. But in general, yes lah. But in this case, yeah, in this case, yeah, we are leaving them. Yeah. In general, sure lah. But in this case, it's just okay. But we're not quite done yet, you know. We're not quite done yet. This is like at the level of Kn here. But we want to do it at the level of TPV. Okay. So we're gonna do more stuff. Let's finish this proof before we're taking break, okay? I have about 5 pages to go. Okay, very short. It's just a bunch of equality here. Okay. So we have established this. Okay, so let's mark it. Yeah. Okay. Let's continue a bit more. So now we'll look at the algebraic affine variety. Sorry, algebraic set. Okay, that we're interested. Algebraic set. Consider set here. Right. Okay, we want to look at some algebraic set ANK. This ANK is basically the Kn we considered just now. Okay. Hopefully you don't forget. But now the inclusion. Okay, so how do we view TPV then? We view TPV as a inclusion into Kn. Okay, so this injective map here will correspond to actually a surjection. Surjection from Kn to TPV. Okay, so this is another algebraic statement which says that if V inject into W, then W star is surjective. Maybe this is one of the statements you will see before we even prove the isomorphism that I told you just now. Is it hard to think about this or not? Okay, direction change is, I think you are quite familiar already, right? Of pullback. Okay, actually, our algebraic geometry is an instant of ALA. Okay, so I let you see it when we do the category just now, before. Is it hard to see this is the surjection or not? Using this interaction. So meaning, if I have a map from V to K, what do you need to do? How to make the map from W to K? Okay. Okay. Did I have a direction wrong? No, right. I didn't have direction wrong, right? Oh, okay, I think it's fine. So V, wait, let me see. So if I have a map from V, I don't have direction wrong, right? Okay. So if I have a map from V to W, and then I have a map from V. Did I have direction wrong? So let me write down. So I have a map from V. And then I have a map from V to W. So how should I map from W to K? Any idea? My claim is you just send, so let's call this I here. You just send P5 B to what it should be, and then other than about other than 5B. Oh wait, before that, maybe we need to talk about what is this map first. Can we even do about this map here? What's this map? Before even we talk about the inverse image. What do you think? Composite. What do you mean by composite? This is not pullback anymore, I think. Okay, this is the pullback thing. Okay, it is a pullback. Okay. So what should we do here for this surjective map here? What's this surjective map? Injection means what? You know how this leads inside W. So if I give you a W map, you want to look at a V map. What do you need to do? You got a W here, right? You got a V here. Yeah, you just restrict. You just restrict. So it's a restriction. Then now you need to prove that this restriction is a surjective map, which is not hard, right? So basically, the inverse image is you just keep what you want for V, and the rest then it to zero or somewhere else. Doesn't matter because this is a restriction. After restriction, this V map here won't remember what you did to other thing than the image of the inclusion. You can send those everywhere as long as it's a number space. Okay, so actually this is a restriction map. And so you just restrict your linear form AN2. Okay, so then this gives a composition here. First, we get the following map. Let's call it D. From MP to MP square. Okay, we know that this is isomorphic to Kn star. Okay, then we can make this longer a bit until TPV star. But this map is also surjective, okay, because it's a composition of a surjective map. I think we will prove there's an isomorphism here, then we will take break first. I scare you cannot put too many things at one go. Okay, so this is surjective, right? Okay, we want to see what's the kernel of this map. Okay, algebra is like that. If you go further next year or go to higher algebra, right? We look at a map, we look at the surjective part, then we ask what's the kernel. Subject image kernel, image kernel, image kernel, image kernel. Okay, then this is what will become a chain complex. Later. Huh? Exact? Yeah, something like exact chain complex, that sequence. Okay, we look at the kernel, image kernel, image kernel, image kernel, image. Okay, so what's the image here? Sorry, what's the kernel? We know it is surjective already. So we want to ask, is this isomorphism or not? Okay, so we claim that the kernel here actually is MP squared plus AB. Okay, so how do we check this? Just a very simple check here. So we just do this simple check. F is in kernel of D. What does it mean here? If and only if your F1P restrict to TPV is 0. Is it true? Because you want to stay inside here, right? Okay, stay inside here means what? You are a 0 function here. Okay, but if you are 0 function here, then you need to evaluate at TPV equals 0. All point. Okay, why is it F1 here? Because this is the first map we map to. Because what will we encounter here? The first part is the linear part, right? You send to a linear part. Second part, just restrict only. That's it. Okay, so you restrict to TPV must be a 0 map. Okay. Because you are a 0 function. Okay. Okay, if you have 0 function on TPV, meaning you evaluate at TPV must be 0. Okay. But if you write this down, what does this mean here? So let's say our FP1 here is equals to the sum of AI of GIP. This GIP is an element in IV. Last time I did a little slight mistake. Let me update you here about this GI here. So last time I told you that the FPI right can be read as a linear combination of GIP here, but that one is after evaluation. Okay, actually it's not directly because if you are function in IV, right, how can you write it as a linear combination over your coordinate ring? Okay, so there's a HI component here. But if you want to do partial derivative, right, what do you do to HI and GI? Both depend on XI. So you need to do product rule. Okay, so if you do product rule, on one side you differentiate your HI first, on the other side you differentiate your GI. But if you differentiate HI, right, you keep your GI. But your GI evaluate at P, what do you get? Because GI coming from IV. So it's 0. Okay, so the first part here goes 0. So the linear part is linear combination over this ring. Okay. Yeah, so this is what we use here. But what does this mean, huh? What does this mean here? So meaning, if you undo your derivative, right? Undo your derivative. Undo it. You undo it. If you undo your derivative, your f and sum here should live inside MP squared. Does this make sense or not? Does it make sense? Does this make sense? If you undo the partial derivative. Does this make sense? If you undo the partial derivative, how? After which line? Oh, okay. So good. You are very good. So this equal to this, right? So the left hand side minus right hand side is 0, right? But this 0 in where? The difference is inside the kernel now. Okay, the difference is inside the kernel. Okay, so if you go back from the isomorphism here, it should live inside the kernel. Okay. Make sense? Okay. All right, very good. And then in this case here, this would be true if f is equal to mp squared plus some IV, because GI coming from IV. Okay. Okay, maybe we'll do halfway here first. Let's take a break until 1:15. And then please, one by one, with your group member, come here and sign it for the Saturday. Week.
我随便签在这就可以了。
对，反正有个记录就可以。你是
对呀、
这个。啥用的？
就多少生病了？
多少病啊？
他应该会去这边上。
啊，他回去几个？
他现在回去了。
他几时回来？
我不知道，他没跟我讲。
OK，呀，
这是什么 presentation 那个？
啊 ，presentation 那个签名。
好的。好。
哎，
还有一点吧，
还有点。呀，
一点讲完了，
一点讲。
希望这有时间吗？
有，12点到2点。
希望能讲完。
是的，
希望能讲完。
肯定能啊。
就把
我们放这样多时间。
到2到6样。
对，对，我们有空间了。啊，我的，你们先传。
是这样，
确定啊？不要对外。
不是5、6吗？email 啊。OK，thank you，thank you。
哦，因为黄色的话，我个人留的比较久的。The block is too small.
啊
The block is too small.
The block is too small.
I'll put my name.
Yes. You say one five. 那个会打发
来一个最低的代理，
14。
全部都会14。
Yeah。Hironaka 的那个 proof 是一个 field method 的 proof 来的。哪一个 ？Hironaka 的 proof。啊，是。像我们要做 field method 做的事情啊。
哦，能做的话就不在这了啦。
把零换成 P。
难怪我看到很多课本很少写那种东西，它只是介绍 blowout 就这样吧。
好sequence 啊，真
我知
的
道 blow 一下会变 smooth， 但我不知道它是一个。
非常难。它只是 proof over characteristic 0啊，over characteristic P 的话就是个 open problem 嘛。他跟我讲说嘛，他叫我把那个 hero 那个体系手把零全部换成 P 就可以了。
某种程度上是这个意思啊。
没有几点。
他8点到5。然后有8个小时，然后加吃饭呢，10个小时。
我问我有没有机会来，要教书啊？
8月。
可能哦，我看大家安排给我了。啊，我要来开，我来不到开个 team 给我。
我肯定开。
OK。
在教课。
这样签，我也3月之前，3月呢？啊？他几时回来？明天啊，这样记得来签啊，明天。
那我组了少很多人。
iPhone 呢？
还不知道。
就在睡觉。没有接电话。 家明天一定要来啊，不然杀进他的那个大家外面。杀到谁？
我啥哟？这不可以有大写吗？奇怪。
不是这种，你是
Yeah.方法是什么？哪一种方法？
这种方法，
看到吗 ？K，对呀、对呀、对呀、厉害。
我不知道要哪个。
然后你就写你要就可以了。
就开个 theory 嘛，其中一个比较简单的一个是比较。我在想说要直接炒，
那个茶叶的话，注意一下谁的组来。
然后我们的
有啊，有 group of T 的，这跟他们 sign 了。
881。
It's a pyro. Don't mess up with my playlist.
Which one is the good one?
然后找别人问，那个人我先上场。
我操！ You got big gold, man. What the fuck?
In Chrome.
Hello. Let's continue. So far, what we have, what do we have here? So let's what we have. MP over MP squared plus IB should be isomorphic to TV star. Okay, we are quite close already. Okay, we know something is isomorphic to TV star already. But we haven't reached our little MP yet. Yes. What do you mean? We quotient by MP squared plus IB. This is what we have shown just now, right? So if you are in the corner, you look like something MP squared plus IB.
It's from a portion to that.
You mean this?
Already count portion for one.
I think.
Oh, I know already.
What do you know? What do you know?
Because this thing already contained because there.
Yeah, IB, there's zero inside there. Yeah, so you are quotienting more stuff. Yeah, okay. Okay, but more conveniently, you should show it that this is isomorphic to MP quotient by IB and then quotient by MP over IB squared. And so meaning you will do IV quotient first. You do an IV quotient first because MP squared contains zero also, right? So you should quotient IV as well. Okay, so I will just split it up. Yeah, we just split it up. So this is a bit different from your fraction. For your fraction 2 divided by 3 plus 2, you can't really do 2 over 2 over 2 over 3, right? Yeah, this is a bit different from your fraction. But this is what we will define as MP bar over MP bar square. Okay, because you quotient by IB. Okay, so in this case here, then to this end, we just need to show. We just need to show MP bar over MP bar square. Okay, is isomorphic to the little MP over MP square. Okay. Well, but not that. Not that. What's this big MP again? Oh, this big MP is the coordinate. Field coordinate I knew driven by the coordinate function, and then now we model by IV here. Not that we have inclusion. Okay, MP is in little MP here because you quotient by IV already, right? Obviously, they should be. No. It's in MP, so definitely evaluate at 0 is 0. Okay, so it's in the MP, little MP. So this inclusion here will induce an injection, okay, on the quotient. I think this one everyone should be fine. It's the just isomorphism thing. No, not just isomorphism, but injection on ring or injection on what is here. Talk about this vector space. This MP bar here, there are a few identity for it. You can view it as a vector space. You can view it as an ideal, which is a module, also can. Okay. But in any sense, this would induce injection on the quotient. Because quotient, you are identifying more things. Okay, so your injection should still work. Because usually it's people subject, right? and then after you quotient, it becomes injection. But now you already inject, then you put things together, still injection. But obviously, you need to respect the quotient in MP squared there. Otherwise your image will get quotient until you don't have the injection. But in this case, should be fine. If you are not happy, right, go back and show this. Okay, try and show not this. Try and show this part. Okay. Try with general. I think general module will work. Okay, and next part, what's left to show if we have injection? We just need to show that phi is actually surjective. So what do we do here? Phi is surjective. So what do you do here? So take an element in your codomain. Okay. Well, we know that it's identified. So f over g may be equal to some other elements in modulo m square p here. So as long as you can have a pre-image that sends to the representative of this class, then you are fine. Okay, so how to find the pre-image here? What's the pre-image here? Do you know what's the relation between MP bar and MP, small MP here? Small MP here got the denominator. But MP bar, MP bar is just really a function coming from the coordinate, generated by coordinate function, quotient out by the ideal of B. That's it. So maybe it's not a fraction form. Even if you have fraction, maybe it's come from the field. It's not really f over g for g inside your k coordinate ring field. Okay, so yeah, so you should think of something that can map to MP or equivalent class of this of f over g. Okay, so the key here is the magic here is to just look at what does this g evaluate to in at this point p. Okay, our point p should be origin, right? Okay, so our claim is f over c. Okay, why f over c here? Because if you look at f over c minus f over g, actually these two are the same thing. Okay, same thing inside MP squared. Sorry? Yeah, why? Can everyone think of why? Everyone think of why? This is a primary school question. I hope. Yeah. D minus G over CG, and then you multiply by F. Okay, so you have at least order 2. Okay, and right, so because what's phi? Phi is induced by injection, right? Really just you put into it. Okay, so you just send F over C to F over C lah. But really, this is living in the same equivalent class of F over G bar. Can I write like this? Like this. Okay, so they are the same actually. So meaning this is equals to F over G in MP quotient by MP squared. In the quotient, they are the same. Okay, because they are differ by the element in the MP squared. Differ by an element inside. Okay or not? Yes.
Actually, we're actually show that MP over MP as a model to keep space. But our claim is MP over where? I mean, if you use one fake thing, always
Wait,
with double cap itself.
wait. What have we done? Let me see. Ah, good. You are good. Very good. You are good. So far, what we have done here is, hence, MP over MP square here is isomorphic to a form of, no, TP. Okay, TPV star. Okay, but what's our goal? Our goal is TPV isomorphic to MP over MP star. So what's the problem here? Can I just put star on both sides? Can I just put star on both sides? Okay, no.
Last thing is
It's not always equal, but it's canonically isomorphic. Okay, so this is another statement, meaning F star star is canonically isomorphic to B. Canonical here means that there's an obvious way you can find this isomorphism. Obvious way you can find this isomorphism. Obvious? Huh? Sorry? Is it obvious? Yeah, ask yourself, is it obvious or not? What is F star star then? Sorry, what is V star star? Star or V star, right? Sorry? You need to have a function to evaluate your function into a number. If you want to build this map is, I give you such function, what number you should take? What's the number you should take? The claim is there's an obvious way to do it. Yeah. If you are interested, you can try think about this. If not, this should be something in ALA. Try and think about this. If I remember, I can put into your tutorial question. Think of this. Okay, so what have we done? What have we done so far? Previously, we defined for you TPV as a zero set. Okay, zero set of some partial derivative equation here. But now, what I told you is, just look at this maximal ideal. And then quotient out by h squared. And then look at the what we call linear function here. This is a dual space, right? The element inside there we call a linear function because we map it to scalar field. Okay, so what we've done here is we extract the algebraic property here. But here, notice when we do this proof, right, we keep on using the fact that this f here actually is a polynomial, so that you can see the order 2 thing, degree 2, after differentiate, you get 0 somewhat. But you can put this definition in differential geometry, right? For example, you can look at the tangent space of your sine, cosine, or even if you want to do complex analysis, also can, right? Also got complex tangent space, right? Okay, but in those cases, can you think about what's the correspondent linear space on? Can you think about it? You think about it? Actually, those are the things in the current research, what they call the D modules. It's invented by Kashiwara. And then Kashiwara got a ever prize this year. This year, ever prize. Anyone know? Kashiwara. Don't know. So don't just learn about Gauss. Who else you know? Gauss. 还在天天跟我讲 Gauss。还有谁啊？哦，不是他跟我讲谁啊？Euler。These are like, 500, 600 years ago, the people already. You didn't know about the current mathematician, Hubert, right? Fukaya still alive, and then Kashmara still alive, right? 那死了这久了，天天讲。我知道啦，因为你们中学在学嘛，这个。But I think to this university level, you should learn more modern maths. Okay, modern maths. Okay. Right. Okay. So far, okay. So this is very important result. So we spend a lot of time proving it here. So the proof here actually uses a lot of advanced linear algebra about dual spaces. Okay, that's it. That's it. But this result here is very important, super important here. Okay, how to relate tangent space to a form space. Okay, so what's the corollary here? Okay, so there's a corollary. So that is a tangent space. Won't change too much, okay, about the neighborhood. So it says that the TPV depends only on a neighborhood. Yeah, so what does it mean by depend on the neighborhood P of P here? Okay, so we're gonna say it rigorously. So let's say if FV to W, okay, is another birational map. Okay, which map? So the neighborhood here is an open neighborhood. We didn't specify open here as what we do in general topology because we already assume these neighborhoods are open. V isomorphically, let's say, to another neighborhood, okay, on your codomain. Okay, if you can do this, then the two tangent space actually is isomorphic. Okay, so to show this isomorphism, right, just now, from what we know, it's just enough to show. Suffices to show MQ over MQ square actually is isomorphic to MP over MP square. Right? We can, if you have isomorphism in dual, actually you can move to V as well. That's the other direction I didn't tell you. Okay, if I need. So can we do this? So if we do this, then we can do it. All right, we can do it as long as we have the double dual is isomorphic to the original vector space. All right, can we do this or not? Do you have map from MQ to MP? Sorry? Oh, sorry, TQW. Oh, this should be TQ. In the book, huh? Okay, I didn't notice. This is TQW. Okay, so do we have map or not, first of all, between this MQ and PQ? MQ and PQ live in where? Function field, right? Okay, so meaning do we have map between function field or not? There's a keyword inside this theorem, right? Birational. So a birational, so isomorphic, right? Equivalence, meaning equivalence on this neighborhood here. If you have a birational equivalence on the variety, what do you have? Or do you have a corresponding thing in the function field? Their function field are isomorphic. Okay. So actually you have map between MQ and PQ. Okay. But the problem here is, does that isomorphism descend to an isomorphism here? So meaning if you vanish on MQ square, do you vanish? Sorry. How the other way around. So if your function yeah. So one thing you have to see is the isomorphism should descend to isomorphism here. Right? Yeah. Okay, so since F W is birational. Birational already include birational equivalence. Birational equivalence. Yeah, birational already tells you that the inverse of this rational map is no. So the inverse of this rational map exists. So it's birational. Okay. Then what we have is we have F star, okay, which is an isomorphism going between KWO, which is KW, to KB. Okay. So last time we know that as long as we have isomorphism on the neighborhood, then we will have isomorphism on the function field. Okay. And then our claim is this descent to isomorphism. And isomorphism, let's call it F on MQ over MQ squared to MP over MP. Okay, but these two are just a duo of TQW star and TP star. But just now we said that we can do a double dual canonical isomorphism back. Okay. Okay. So so in this case here, we relate dimension. Sorry, we relate two tangent space on two variety here, which are birationally equivalent. Okay, so if you can relate the two dimension of tangent space here, meaning what? If V and W are birationally equivalent, okay, let's do this double arrow on this dotted line. Then actually this two dimension is the same, because dimension are defined using the minimum of tangent space, but we can map tangent space right and across. Okay, and then this special map here. So this special map here that we have on MQ over MQ square, MP over MP square, right? So this is the phrase you should see. If FV to W is a morphism, okay, such that FP equals to Q, okay, then we call the map we built from the birational property, say the dual map, okay, of this F star bar here. Okay, this F star bar here should be going from MQ star to MP over MP squared. Okay, basically what's this F star bar doing? You pull back first and then you look at the map on this portion. So there's a bar on top. Okay, because if you close the quotient, right, this is just the map on the function field level. And then after you add the quotient in, then you have a quotient module map. or quotient vector space map. So this will give us a homomorphism. Okay, so it's like what we did just now, you need to go through some dual stuff to get, you apply the isomorphism, and then you get back your map from TPV to TQW. So for instance, just now we have this F star bar right across this. Okay, but then how to go from TPV to TVW? How? How? Can you just do like this? Isomorphic to TP. Oh, I think is it the wrong direction there? Is it correct or wrong? Oh, dualize, then turn the other direction. Okay. So what am I doing here? Right. Can I what can I do? Can I go back to TW here? Is it possible to go back to TV here? If I want to go back, what should we do? So let's say we apply this homomorphism. There's a F star bar on, yeah, just call it F star bar for the moment because isomorphic. Or if you like, okay. So let's say this one is H, this one is G. You compose this isomorphism. So how to compose this isomorphism here? You so let's say H go down, G go down. So you do H inverse and then G. A bit like diagonalization. Okay. But you want the map from TPW to TPV. Can I write like this? It's not right. But what can we do? We can further dualize. Dualize. Yeah. You look at the dual of these two. And then after you take in the dual, then this thing need to be stop direction. Okay, so that's why we have this direction here. Okay, because at the top here, this is equals to TQW dual, right? And then the other side is TPV dual, right? But you do again, then the function change direction. Okay, so you see, you do twice. See, the DF is a map from the space of TPV to TPW. Okay, you do twice. So you get the same direction from your F. Same direction. If you have a map from V to W, then your DF is going from DPV to DP. Same direction only. Okay, and then this is what we call differential. Okay, differential of F at P. Hey, the differential and differential geometry, what you do? You know? You just df of partial f partial x dx like that, right? Okay. But this differential is actually the differential that you will see in the complex or real analysis. Okay, it's 44. Okay, good. All right. Next, we'll talk more about algebraic property here. There are more things we're not going to prove that's coming from commutative algebra. Maybe I'll write it into your tutorial. Okay, so if V is an affine variety here, okay, then we get dim V equals to coincidental degree, okay, on cleavage. Why? How to show this? How to show this? So far, what we know, okay, Lydia 看到这个我也是不懂怎样做， 但是我记得我刚才做过什么？我刚才做过什么啊？来上过厕所？哎，不是，我刚才 prove 过什么？What do you have proof for transcendental degree just now? What do you know? 啊？什么 elementary? Yes. What's the V here? What's the V there? What's the V? Just now. Huh? Only got one F, right? Defined by one F. What kind of V is that? Start with H. What's the variety defined by one F? Huh? Hypersurface. So we know that this statement is true for the hypersurface. So can you link affine variety to hypersurface? Induction. A bit too much. Got lah, intersection of finite hypersurface. But we know that every affine variety actually is quasi-projective variety. But we know that every variety actually is, we show that P actually is birationally equivalent, okay, to an affine hypersurface. Okay, just now we said that affine variety is a finite intersection of hypersurface. That one is wrong. Okay, this one is not just isomorphic. This one is just equal already. Okay, equal on the loss. But this one is just birational. Okay, this one is pretty important. Quasi-projective variety is already birationally equivalent to a affine hypersurface. Is it affine hypersurface? Yeah. I hope I'm not wrong. Okay. So it's very important here. Then, so V has the same dimension with an hypersurface. Because they have isomorphic function field F, what we have produced just now. No, not by what we produce, by the birational equivalence. Because they have isomorphic. Okay, and then the proof will follow. Okay, then the corollary is for every affine algebraic set V, okay, the set of smooth points is an open-ended set. I forgot. I think the book didn't provide the proof. I forgot why I didn't write it here. I thought I would do on spot, but no time here, so I just left it for exercise. Hopefully, I can fill it into my notes. We didn't establish this last time, right? We did talk about a smooth point on affine variety. And then what else we talk about? Affine variety, hypersurface. Yeah, that's it. We haven't go to this genre yet, but it is actually an open dense subset as well. Okay. In this case here, should we do more? We will do more, but I won't write it down anymore. Let's quickly mention them. So let's see. So we could define smooth or regular on a quasi-projective variety as well. Previously, we just do for affine variety case. How do you do it? You need to look at the affine neighborhood. So what is the affine neighborhood here? Meaning it's a open neighborhood, but it's an affine. Open neighborhood in affine. So you should use the standard affine covering to see the affineness. And then so again, yeah, okay, I think that's it. Again, you can show that the smooth point of quasi-projective variety is also an open dense set. Okay, open dense set. And then how do you define dimension there? Basically, you look at the pieces, okay, of this standard R5 covering here, and then you check dimension there. And then the proposition is these intersection, right? These pieces, right, should have the same dimension. Okay. So V in all these pieces should have the same dimension, and then we call this a dimension V. So this is actually a proposition. You need to prove why are they the same? Why a priori they should be the same? So if V is reducible, we also look at the maximum. Okay, so this is how we generalize to general quasi-projective. Okay. Okay, so far. Any question? So you see how we already looked at the very general variety here. Actually, smooth point is not a very big deal. What do I mean by that? Actually, most of the point inside your variety should be smooth. Okay, singularity actually is a small part of it, small part of it only. But actually, this small part, right, spark a lot of research interest at the moment. Okay. Any question? Before we break. Okay, if no question, I will see you tomorrow. Oh, by the way, this afternoon got actually algebraic geometry seminar. What's the topic on? Algebraic conjecture. What is it? Singularity stuff or what? I forgot. I read it. What's the anyone know? Algebraic. So it's the author of our textbook. Conjecture by him. Okay. If you are interested, you can come 3:30.